Hey everyone, in this video we're going to be talking about linear differential equations. So we previously talked about linear differential equations, but now the difference pretty much is that we're going to be incorporating what we've learned about linear algebra and matrices in this process, and then also we're interested in higher order differential equations than we've looked at in the past. So in general, here is a linear differential equation of order n. So remember, our differential equation involves derivatives, and this is saying it goes up to the nth derivative. So a quick note for you on this notation: anytime you see what looks like an exponent but it's in parentheses, that's actually derivative notation. So this is saying the nth derivative of y. This is saying the n-1 derivative of y, and all the way down to the first derivative and 0th derivatives. So this is our linear differential equation, and the order is n because it goes all the way up to the nth derivative. All right, so some things about this equation. In this case, the independent variable is going to be x. The dependent variable, what depends on x, is y. And then a sub n minus 1, all the way to b are functions of x only, so they don't involve y at all. And then when b equals 0, whenever this whole equation equals 0, that's going to be our homogeneous equation, which we'll focus on that for the majority of what we're going to talk about. And so what we consider standard form for our linear differential equation is this format here, where pretty much we just divided every term by a sub n. And so if you want to break down what these p's are, p sub 1 is just what we get from dividing our a sub n minus 1 by a sub n. Okay, so notice right here you would divide a sub n by itself. So there's an invisible 1 right in the front right here. And so p sub 1 is dividing this coefficient by a sub n, and you do that all the way down. So p sub n would just be a naught divided by a sub n. Okay, and then we're changing g from b to g basically because we're saying b sub x divided by a sub n. So that's what we're calling g of x. Okay, and standard form here also requires that p1, p2, and all the way to g are continuous. And this is on some interval, and we'll do an example where we find this interval. And so a linear higher order differential equation initial value problem always has a unique solution. So let's try out this example. We have an initial value problem here, and we're going to find the interval or intervals that guarantee the existence of a unique solution. So first, just identify that this is in fact a differential equation that is linear, and it is an initial value problem. Okay, notice where we have up to the third derivative of y. All of the coefficients only involve x, our independent variable, right here, 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 and then over here what this equals is something that only involves x as well. Okay, so we have up to the third derivative of y, and we also have some initial conditions. And remember, to be able to solve an initial value problem, you have to have up to one less than the derivatives present in your equation. So what I'm talking about here is, because this is a third order differential equation, we have to have initial conditions up to the second derivative to be able to solve this. All right, so first we're going to write this in standard form, which just requires that we divide every term by this leading coefficient, which in general I was calling a sub n. So if we just divide every term by this leading coefficient, this is what we get. And anytime you can, simplify, just do a little bit of simplification. So I just divided out some x's on a couple of the terms. So this is standard form of our differential equation. Now what we want to do is we want to find the intervals, if there are any, where p1, p2, and so on are continuous. So in this case, we have just a few terms to work with. This isn't too long. So let's break them down. P1 is this coefficient here, p sub 1. And notice that this is defined as long as x is not 1, because otherwise you'd be dividing by 0. And so you can say that this p sub 1 is continuous if we just jump over 1. So anything from negative infinity to infinity, but you have to jump over 1. You can't include 1. Then p sub 2 is this coefficient here. Same exact process because the denominator is the same. So x can't be 1, so it's continuous on this interval. And then p sub 3, this coefficient here, This one is defined only when x is not 1 and also when it's not 0, because either one of those numbers cause this to be a 0 on the denominator. And so we have to jump over both those numbers. So from negative infinity to 0, jump over 0, from 0 to 1, jump over 1, 1 to infinity. And then our last term here, what this equation equals, this is what we were calling g, or g of x. This one has a few conditions. X can't be 0, x can't be 1, because that would make the denominator 0. But also, the square root inside the radical can't be negative, otherwise it'd be imaginary. So x has to be negative 5 or more. So we put all those conditions together, and so the interval where this term is continuous, it starts at negative 5, not negative infinity, because that would give us some imaginary numbers. So we can go as small as negative 5, then we have to jump over 0 again, jump over 1, and then that's what we get there. So what we want is we want an overlap of these intervals where our function is continuous. And so normally what you do, it's the thing that has the most, like restrictions. In this case, it's going to be g. So the answer here is that the differential equation is continuous, and therefore unique solutions exist on this interval from negative 5 to 0, and then from 0 to 1, and then from 1 to infinity. And what I was just saying was you basically pick the one with the most restrictions, but you do need to make sure it overlaps with the rest. So if you think about it, this interval that I have down here as the final answer, it also incorporates these other intervals. Okay, so all of these are also included here, but this one has the most restriction. So we have to pick that one because we can't include, like, let's say negative 6, like this one here would include negative 6, and so would this one, and so would this one, because it's not included for g. It would make g undefined or technically imaginary. Okay, so now let's talk about our homogeneous linear differential equations and the representation of solutions. So the nth order linear homogeneous equation looks like this. Notice the difference is just that this is in standard form already and it equals 0. So it's homogeneous because it equals 0. And it has n solutions. So these n solutions are linearly independent. And so we're writing those solutions as y1, y2, and so on, all the way to y sub n. And every solution y has this format if you want to write it in general. So each y can be written as some constant, c1 times y1 plus c2 times y2, and so on. So that's our general solution. And it's just a linear combination of the other solutions. Okay, so our fundamental set of solutions is going to have the following. So any set of functions, notice we have y1, y2, and so on. These are what I'm calling the solutions. Okay, these are our n solutions to this differential equation, this homogeneous differential equation. So our set of functions is our set of solutions if the following three things are true. N, the number of solutions, must equal the order of the differential equations. So if this was a third degree differential equation, third order differential equation, there would be 3 functions in our solution set. Each of our solutions, so each y sub I, must be a solution to the differential equation. That one's kind of a given if we're calling it a solution set. And then y1, y2, and so on, they all actually must also be linearly independent. So all of those 3 things satisfied, and that gives us a solution set. And so all possible solutions can be constructed from this set. All right, now the next thing we're going to talk about, because we're going to be using it in this process that we go through, is what's called the Wronskian, which is this determinant right here. So here's our definition. f1, f2, and so on are n functions that are n minus 1 times differentiable. So real quick note on that, if this is a 3, then that means that it's differentiable up to the second derivative. If this was a 4, we would be able to differentiate 3 times. The Wronskian of these functions, f1, f2, and so on, is the determinant. So by definition, the Wronskian, or w, of these functions is this determinant here. So notice a couple things. We have our vertical lines. That's denoting that this is a determinant and not just a matrix. And we have row 1 consists of the functions, row 2 consists of the first derivatives of the functions, and then we just start taking derivatives going down. Second derivative in row 3, third derivative in row 4, and so on, all the way to the n-1 derivative, depending on whatever n is. So if we have n is 10, then this would be this last row would have the 9th derivatives in it. Okay, so some facts about our Wronskian and how it affects independence and dependence. So for some x naught in some interval, I'm just calling it a to b, if the Wronskian of that value is not 0, then our functions f1, f2, and so on are linearly independent on that interval. Then if at least one of our functions is a linear combination of the others, so another way to say that is that if we can write this equation here, c1 times f1 plus c2 times f2 and so on equals 0. And as long as one of these coefficients is not 0, so they just can't all be 0, as long as one of these coefficients is not 0, then that's a linear combination. Okay, that's saying one of our f's can be written as a combination of the other ones. That means that f1, f2, and so on are linearly dependent, and the Wronskian is equal to 0. Okay, so just a couple of ways to talk about the same thing. So if now we're saying a function equals y, so we're saying that our functions represent the solutions to our homogeneous equation, then either the Wronskian is not 0 for every x, or it is 0 for every x. And moreover, what that implies is that if the Wronskian is not 0, then our set of y's, or solutions, is linearly independent. And if the Wronskian is 0, then our solution set is actually linearly dependent, the set containing the y's. Okay, so a lot to take in here, but basically what you want to just pay attention to is what happens when the Wronskian doesn't equal 0 and what happens when it does equal 0, and how that affects linear independence and dependence. Okay, so let's try out this example. We're given 3 functions, f1, f2, and f3, and we want to show that they are linearly independent. And we're going to do this 2 ways. We're going to do this part A if the functions don't necessarily represent solutions to a linear homogeneous differential equation, and part B by claiming that, yeah, they do actually represent solutions to a linear homogeneous differential equation. So we've talked about linear independence and dependence in the past, so we are relying on some things we've learned previously to be able to keep talking about this. That's that whole thing where I was mentioning a linear combination. So let me remind you, because here it is. If you can write this equation, c1 times f1 plus c2 times f2 and so on equals 0, and as long as all the coefficients are not 0, then the functions are linearly dependent. This is by our definition of linear dependence that we've learned previously. And so what we want to do is, by using this fact and trying to show that they're actually independent, we want to show that they are all 0, these coefficients, c1, c2, and c3. Meaning that when we have this equation right here, c1, f1, and so on equals 0, the only answer to this is the trivial solution. And the trivial solution is that everything's 0. And so therefore, our functions are in fact linearly independent. So we're basically using our fact right here about dependence and doing the opposite of it. We're trying to show that these coefficients are all 0 so that we get independence. Okay, so taking our equation, our linear combination here, we're just filling in what we're given. This was f1, this was f2, and this was f3. And let's just do a little bit of simplifying. Okay, distribute, and a little bit of rearranging. And so what we have here, we're trying to figure out what c1, c2, and c3 are. And so we have 3 unknowns. So we need a system of 3 equations involving those 3 unknowns. So what you can do to figure this out is pick any values for x. I just picked x is 0, x is 1, and x is -1. And I've just plugged them into this equation right here, this last equation. And so that gave me 3 equations right over here on the right side of my arrow here that involve our unknowns. our C1, C2, and C3. And so from there, we can use our augmented matrix to solve this system of equations. Okay, so equation 1, notice it's 0 for C1, 0 for C2, 1 C3 equals 0. That's equation 1 right here. Okay, and then row 2 represents equation 2. Row 3 represents equation 3. And if you just rearrange and row reduce this matrix, you're going to get the following, which says that C1 is 0, C2 is 0, and C3 is 0. So therefore, all of our coefficients were 0, which is the trivial solution to this equation, implying that our functions are in fact linearly independent. Okay, so for part A, we pretty much were relying on things we've learned previously, how to solve an augmented matrix, and our facts about linear dependence. And now part B, we're going to use the new stuff. We're going to use a Wronskian to solve part B. Okay, so for part B, we want to show that the Wronskian is not 0. And then that will give us that we have our linearly independent set. Okay, so setting up our Wronskian, remember how this goes. Row 1 is just your given functions. So notice the first spot here, the first entry is just f1. The second entry is just f2. Third entry is f3. But then the second row is your derivatives, first derivatives. So differentiate x, you get 1. Differentiate x squared, you get 2x. And differentiate 1 minus 2x squared, you're going to get negative 4x. And then the third row, which is our last row, is the second derivatives. So derivative of 1 is 0, derivative of 2x is 2, derivative of negative 4x is negative 4. And so if you want to, you can double check. This is where we would stop because this was, we had 3 functions here. And so we can only go up to the second derivative. So this is technically the 0th derivative, first derivative, and second derivative. Okay, and then we're finding a determinant. So what you can do here is do your cofactor expansion across any row or column. I chose to do my cofactor expansion across row 3. So let me remind you about that really quick. So my coefficients were 0. And then remember to alternate your signs. So positive 0, negative 2, plus negative 4. And then remember how that goes. You cover up the row and column of that coefficient. So negative 2 times the determinant of the 2 by 2 that we get from deleting the row that 2 is in and the column that 2 is in. So it leaves us with this 2 by 2 where we have x and 1 in column 1 and negative 1, or sorry, 1 minus 2x squared and negative 4x in column 2. And then remember, because it's a 2 by 2, just trying to remind you of things you've seen before. The determinant of a 2 by 2 is really nice and easy. So, sorry, let me just write this down. It's just going to be diagonal down right minus diagonal down left. Okay, so x times negative 4x, and then minus 1 minus 2x squared times 1. Okay, just reminding you about that determinant. Okay, and then same thing for the last term here. Negative 4, you cover up the row and column, and you do the determinant of the 2 by 2 over here. After some simplifying, we're going to get that that whole determinant becomes 2. As long as it's not 0, that's good, because that's what we're hoping to show. And therefore, because the Wronskian was not 0, then our functions are linearly independent. And that's because we were told they represent solutions to our homogeneous equation. Okay, so that's what we wanted to talk about mostly. The last thing to show you is what happens with the non-homogeneous case. And so we have for the fundamental solution set containing our y's, y1, y2, and so on, corresponding to our homogeneous equation. Okay, notice it equals 0, so that is our homogeneous equation. Then every solution to the non-homogeneous equation, notice the difference, it equals something else, not 0, it equals g of x. It can be written as y equals y sub p plus this linear combination we've been writing before. Okay, and this is where y sub p is just a particular solution to the non-homogeneous equation. So very similar to the general solution for the homogeneous equation is what we have right here. The difference is that for the non-homogeneous case, we add in this particular solution for the non-homogeneous case. So homogeneous if it equals 0, non-homogeneous if it equals something else, and then we add in that particular solution. Okay, so that's it for this one. Thanks for watching.